All right, let's talk about chapter 6. So now we're going to talk about things moving around in circles. So we've gotten all our kinematics equations down for, straight lines and things. We're going to talk about a little bit about things moving around in circles. Okay, so the first thing we have to do is come up with a new distance. Okay, normally if you go from point A to point B, we say that's you moved a distance x. Okay, now what we're going to do is if you go around along an arc, for example, we're going to measure that with an angle. What was the angle that you moved? That angle here. Okay, why? Because when you go around, you go 360 degrees. If you go around, oh cool. If you go around again, that's another 360 degrees. If you go around again, then, how cool is this? Yep, okay. Then you get another 360 degrees. So if you go around 3 times, that's 360 degrees, degrees times 3. And if we measure it in radians, every time we go around, that's about 6 radians, 2 pi radians, times 3. If you went around 3 times, then that would be 6 pi radians around would be your distance. So we got a new way to measure distance, and it's theta. Now the relationship, this length here that you travel is called s. It's called the arc length. It's related to r times the angle. Whatever r is, your radius, times the angle that you move, r times theta is this arc length. Okay, so that's the relationship between those two things. As we go forward, we'll use that information. Okay, now if you go all the way around a circle, the circumference there is 2 pi r. Okay, and then this arc length here is s, but then you have this length r here as well. So if you make s equal to r, okay, then you end up with your change in s all the way around, 2 pi r divided by r gives you this 2 pi thing. So if you go all the way around, your total s is 2 pi r. So you get 2 pi r divided by r, and that's where one revolution all the way around is 2 pi. Okay, so that's where we get this definition of the radian. If you go all the way around a circle, that is 2 pi radians. That comes from that. Okay, so 1 radian, it's also easy to measure. 1 radian is if you make s equal to r, okay, then you have r over r. That is 1 radian by definition. So your angle theta, if this is r, that's r, and your arc length is r, then this angle is as defined, literally that's how the radian is defined, to be 1 radian. It turns out that 1 radian here is about 57 degrees. Okay, 57 degrees is your radian. Okay, so there's some other measurements here. Divide a thing up into 6 parts, you get pi over 6 radians, whatever. Halfway around is pi radians. So the way I like to think about this is there's your thing. You go up 1 radian, you measure another. So this is 1 radius. There's 1 radius. Along here is 1 radius. You go along another radius, that's another r. You go along another radius, that's another r. Let's get back to the thing. Okay, so 1r, 2r, 3r, another r. But then you get this little bit extra here. So you have 1r plus 1r plus 1r. You get 3 radii. 1, 2, 3. But you need a little bit more to finish this circle off. You have 3.14159 blah 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 radii. So you can fit 1 radius, 2 radius, 3 radius, and a little bit more will get you your halfway around a circle. That's 3.14159 radii around. So what is that? That's pi radians. Okay, so that's pi radii to go halfway around a circle. All the way around this angle is pi radians, 3.14 radians. And then 3.14 to get back around, that's what you get the 2 pi from too. Okay, so that's what a radian is. It's not a big deal. 1 radian is about 57 degrees. That's just, what a degree is. There's 360 degrees all the way around. and then 1 radian is 57 degrees. All right, so then we have to come up with some new variables. If we know that if we want to talk about this angle changing, okay, changing over a certain amount of time, that's defined as the angular velocity. So rather than meters per second, now we have radians per second, and that's angular velocity. So now we can talk about how quickly something's orbiting around. I'm using radians per second. Okay, if we want to go between a velocity, which is if we want to talk about something actually moving along that arc at a distance r, then what we care about is the arc length, 2 pi, not 2 pi, s times the angle is this length here. Sorry, r times the angle is equal to s here. So if we know our angle and the radius of our motion, then we can get the total distance we travel, s, and that's just r times theta. And then r times theta divided by time will give our actual r times theta divided by time is r omega, and this is our relationship v is equal to omega r, where we can translate between angular velocity and thinking about how fast the thing is actually moving at the tip of this rotation. Okay, so yeah, we got a car wheel here, for example. Read through that example, and you've got a record player and a fly on it for some reason, moving around. Okay, so centripetal acceleration is now change in velocity over change in time, and you can see what happens. We've got a velocity vector here and a velocity vector there. If I do the head-to-tail method on those two vectors, then we have a delta v. In order to take v1 and bend it down this direction, we had to go a certain amount. We had to apply an acceleration to grab that vector and pull it down. So the change in velocity divided by time is your acceleration. Okay, so angular acceleration, centripetal acceleration, turns out to be v squared over r, the magnitude velocity squared over r, and then we know that v is equal to omega r, so we can replace that, and we have our two equations for acceleration in terms of radians per second or meters per second. So in this case, centripetal acceleration in meters per second squared, and in this case, radians per second squared. And that's just those two calculations. All right. Yeah. Blah, blah, blah. Okay, so centripetal force, we know what acceleration is now for centripetal acceleration. Centripetal force is just ma, or just ma centripetal, and so then a is mv squared over r, a is v squared over r, or r omega squared. So the centripetal force is either mv squared over r or r omega squared. The centripetal force then is the force required to keep something moving around in a circle. That's what this force is. If you want to know, when you go around a curve on a highway, what force you need to apply to stay on that curvature, it's m times your velocity squared divided by the radius of that curve. Okay, so if you want to determine, the max force, the max speed you can go around a curve, then you can, you'd have to know the max friction force that your tires could withstand and solve for v if you know the radius of curvature of the curve. So that would say that's a 10-meter radius of curvature or something like that, which means it would be like a circle that has a 10-meter radius, and then you want to drive along that. Well, if you go too fast, you're going to fly off. But if you go the right speed to balance out so that you maintain that centripetal force that keeps you on the curve, then you're good. So, yeah, blah, blah, blah. Blah, 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 blah. Okay, so this is an example of trying to keep a car on the road. You're going to use the normal force of the car times the mu sub s to keep the car on the curve. And that's what a banking curve is you use the static force in this direction. And the reason you use the static force in the direction there is because your car should not be moving up or down if you're in an ideal curve, banked curve, and ideally moving. So this car, gravity is going to want to pull it down this way. A force of friction is going to be pushing back that way. And then those two forces are going to balance in order to keep this thing on a curve. Okay. So let's continue. 6.4. So fictitious forces are interesting. This is when you you put a grapefruit on your dashboard in your car, you turn left, and it looks like the grapefruit just gets a mind of its own and wants to fly away. So the grapefruit is obeying Newton's laws that an object in motion stays in motion unless acted upon by an outside force. In that case, you turn the car experiences a force, but the grapefruit does not. So it wants to continue going straight. So you just moved the car out from underneath the grapefruit, and it ends up flying away in a different thing. Okay, so that's what fictitious force is. And yeah, so anyway. Blah, 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 blah. We've got some other things talking about forces, central forces. Okay, so Newton's universal, again, you're supposed to read all this. It's pretty self-explanatory if you read it. This is a review that you should use. You should watch this before reading it, but then you should go back and read it. All right, so 6.5, Newton's universal law of gravitation. So the idea here is that Newton, an apple fell and hit his head, and he realized that would be the same force that keeps the moon around the Earth or the Earth around the sun. The same force that draws the apple down draws the planets towards each other. And that's the force of gravity. Force of gravity is depends on the masses of the two objects and the distance between them. That's it, m1, m2 over r squared. G is this constant. It's unchanging. It's a parameter. It doesn't change. So if you want to know the acceleration of gravity, there it is. It's the mass of the Earth times the gravitational constant divided by r squared. So you can solve for that, and you get your 9.8 meters per second squared when you're at the surface of the Earth. If you go down into the Earth, the gravity goes up. Well, not up, down. And if you go further away, the gravity goes up. Actually, the gravity's going to stay the same. If you go far away, the gravity starts going down, okay? Which is kind of cool. La la la, next things, etc. Blah blah blah. We got the tides, right? Spring tides and neap tides. So when the moon and the sun are on the same side of the Earth gets heavily deformed by the gravity, and you get a very high tide called spring tide. When the moon is on the opposite side, you also get a high tide, very high tide. This is the highest tide you get is during a new moon phase. The next highest tides you get are during a full moon phase. And then the neap tides are when the sun and the moon kind of, they don't work as well together. So your tides are not as high as normal or in the other cases. Yada, yada, yada. Da, da, da. So Kepler's laws, you got 3 laws. The first law is that planets orbit each other in ellipses. So the sun is here, Earth goes around the sun on an elliptical curve, not a circular curve. Second law was that, this planet, when it goes here in this part of the orbit, it goes faster than out here. It goes, you. That's what the second law says. So it says it sweeps out equal areas. This area here equals this area here. And it does that in the same amount of time. So the time it takes to go from here to here is the same amount of time it takes to go from here to here. So when it's further away, the longer leg means it has to travel less this way to cover the same amount of square footage as this does. Okay, so that's the second law. The result of that is it moves fastest when you're closest to the object. And the third law says that the further away the object is, the slower it orbits. So Mercury goes around the sun, we go around the sun like, and Neptune is like, taking a super long time to go around, 150 years or something to go around the sun. So there's your equal areas, second law thing. Yeah, derivation of, forget about it. Blah, blah, blah. And yeah, we got our planets here. Cool, thanks. Yeah, the Earth this is the Ptolemaic view, the geocentric view, which is Earth at the center and all the planets do their weird orbits. The Copernican view is that the sun is the center and we all orbit around it, and that's called the Copernican revolution when we realized that was the case, and the folks were upset about it. Okay, that's the end. Talk to you later.